Hello and welcome everyone. In this particular class, we will learn about the regression basic, what kind of regression analysis you can do. We will cover simple linear regression and as well as logistic regression. So we'll cover both modules, module 4.6, which is all about simple linear regression, and the module 4.7 which discuss about the logistic regression. Both you will able to know what are the basics behind it and what kind of method needs to use in different conditions based on the data sets, based on the research question and hypothesis you have in mind. So are you guys ready? Let's start. So let's start with the first simple linear regression. So if you already know about this, regression is simply interpreting the coefficients, verify the assumptions and diagnose the issue. Regression, you do a regression modeling to fit a line between the response variable and the predictor variables. Learn how to fit models, understand the residuals and communicate results with appropriate uncertainty. That's the overall purpose of any kind of regression model, specifically in simple linear regression when you are trying to do bivariate type of analysis. Here what we learn, the objectives for us is fit and interpret the simple linear regression model. That's the one thing that we learn. Second, check line assumptions. So line assumptions is all about linearity, independence, normality and equal variance. So we'll check all four in the regression line plot or regression model, how we can use this information. Then use residual diagnostics to evaluate the model fit. This is also very important. And last is the regression results with the appropriate uncertainty. We will how to communicate this information to anyone, like with your colleagues, team member, or wherever you are presenting those regression results. So model and interpretation, first thing. So in this, you guys have heard of this formula, which is y is equal to beta 0 plus beta 1 x plus e. This is a simple linear regression, relates the dependent variable, which is here is a y. So whenever we'll say dependent variable, means the value of y is dependent on something, okay, to the predictor variable. So here the predictor variable for us is the x is the predictor variable. So y value will change based on the value of x. This is the fixed thing here. Then there are certain things like beta 0 is intercept. This is the intercept. So intercept is value of y when x is 0. So when you know the value of x at that place, you know the value of y. So that's how you define the intercept in the data. Once you know the intercept, then you do for beta 1, which represent the expected change in the y for 1 unit increase in the x. That is very important. How you will learn this? You have the x values, you have the y values, you want to understand the linear relationship between the x and y. So you need to compute the beta 1 value for the each expected outcome change in the expected by the 1 unit change in the x values, the observations that you have. This will capture in the beta 1. Then you have the this symbol which captures the unexplained variability, and that symbol you can change whatever you want, but this is all about the random error, the unexplained variability that you will get from the data while computing those linear regression. So this is the complete formula. You will have the value of x, you will have the value of y, then you will go for the value of x, and for that you will predict the value of y. This is the ultimate purpose. The best fit model will predict the good predictions with less variability, or like will have less unexplained variability. That means will have less random errors. So those kind of things you can decide from. Now, OLS estimation, when you have done the linear regression, you have made the fit and everything, how you estimate this? So first is the minimum SSE. Minimum SSE is always a sum of squared errors, which is you can find from beta value beta 1 to minimize how you will get the minimum SSEs. The second is the R square. R square is the variance explained by the model. So whenever you will see any regression model, you will see they will report the R values or R square values. These R square values are the one which help you to determine that how strong the relationship is, how strong the closer to one, the stronger the association. Now, variance explained by the model divided by total variance in the data, that defines the total R square. So let's say in your data, the total variance is always 100% variance. Now, variance explained by the model is close to around 60%, 65%, 70%. So what will be your R square? Now 65, 0.70, 0.75 depending on. The greater the R square value, that means your model is able to capture the maximum variance that is present in your data. So that's a very, very good measure that people use in the regression analysis. Now the residuals. So residuals are always like y minus y observed versus predicted, key for model diagnostics. So these residuals are important apart from the r square, that what other information you can get from the observed minus predicted values. And this is good for if you are observing the diagnostics of the model, different parameters, co-founder, covariates. For that, this is very good. That is very good variable to identify. Then visualize the fit. Ultimately, when you get the sscs, when you get the r square, when you get the residuals, then you need to plot it on the scatter plot, and then you need to visualize the fit, how the data is fitting for the x and y axis, how the regression line is coming. Is it a continuous line? Is it the line that will help you to make the predictions in the future? Is it not the random line? So those kind of decisions you can make from the regression type of lines. Now, addition, if you remember, we discussed about the linearity, we discussed about the independence, we discussed about normality, and we discussed the equal variance. So those kind of things you can get from the fitted lines. First is the linearity, residual versus fitted. So here are your fitted values, and you are trying to put the values on the regression line. There is no pattern. If you're getting some kind of curve or something, that can be bad. No pattern sometimes can be good for the linearity predictions, because in the linearity you are not expecting anything to be changed. If you will get some kind of curve like down or up, that means there is some relationship. There is no linearity. Right now the linearity is trying to identify them for the x-axis value, by axis values are not at all changing, so you will get a constant values, constant patterns or something. Now the independence. So in the independence, when you are doing residual versus other, random is good, but pattern is equal to bad. If you're getting something random in the plots, in the dot plots while collecting, that means it is showing a good independence of the data. Then it comes to the normality. If every point are in the line, that means if x axis is increasing, y axis is also increasing, y values are also increasing, all the points are perfect in the line, that is the best plot that you can get. Best regression, predictability will be good, there will be less chances of error and everything. Then the equal variance. So in the equal variance, you get the constant spread. If your constant spread is equal to good, then the funnel shape you are getting can be bad. So equal variance is also providing the information about how well the fitted the model is. So these kind of plots you use the plots for linearity, for independence, for normality, and for the equal variance. And by just plotting this, you get the idea about the data, how the data is fitted, how the model is fitted, what kind of outcomes, what kind of predictions these models can make. Okay, you can read about these things if you want. Linearity is residual, so no pattern. Independence, residual, uncorrelated with each other. Normality, residual, follow normal distribution. Equal variance, consistent variance across all fitted values. Now then you go to the coefficient meaning and the confidence interval. We have already learned the confidence interval thing. We calculated the confidence interval from the mean, we calculated confidence interval from the distributions. And so here what confidence interval indicate is the precision, which is like prediction versus mean response intervals. You can get the practical versus statistical significance also. So regression coefficient interpretation. So regression coefficient interpretation is a simple line in which beta 1 represents the slope we discussed already, which is expected change in y per unit of change in the x. When you know this value, how much is the expected change, when you know the slope, then for each x value you can predict the y values. And this is simple formula in which you need to know the x, slope, and the intercept, the changes that you are expecting, and those things are more than enough for you to compute any y value, predict any y value. Then the coefficient interval for the coefficients. Again, 95% of coefficient interval provides the range of plausibility of the values for the true slope. Narrower interval indicate more precise estimate. However, if you are getting the broader interval range, like if the interval range is very short, that means you have a good estimates, you have less uncertainty in the predictions. But when you are getting higher numbers or higher range, then you will have more uncertainty in the predictions. Now then, predictions versus confidence interval. You're getting the confidence interval first thing, now you're making the predictions. So confidence interval is estimating the mean response, what you will get, in what range you will get. But prediction interval predict individual observation and are always wider. Prediction interval can go beyond the ci confidence interval. It can be lesser, it can be higher, it can be in the same range. And that's how based on, you have your confidence interval, you have your prediction interval, and based on those predicted value, you compute the r square, you compute the significance, you compute the predictability of that particular model. The significance, again, statistical significance doesn't imply to the practical importance, but consider the effect size and the domain effect when you are doing any kind of regression analysis. How you will check the linearity? When you created a regression model, for linearity check, you will plot the residual versus fitted plot, reveal the non-linear pattern if there is any. If the model fitting is very poor, consider different kind of transformations in the data for curved relationship. If you are getting any type of curved relationship, not direct relationship, very broad relationship, so you can try different kind of transformation like log transformation, square root transformation, log n transformation, double square log transformation. Those kind of transformation can arrange the data in limit numbers, and then you can try those relations again. Any type of polynomial terms when relationship shows consistent curvatures, you can try that. Non-linear patterns in the residuals indicate bias in the predictions. So you should not get too many non-linear patterns in the residuals. Otherwise, if you're getting, then that means there is a bias in your whatever predictions you are making. Now, after making the predictions, you have the fitted regression line, everything, you understand what kind of relationship is there. You need to identify the outliers, and then you need to leverage that and influence your model. For getting the outlier or detecting the outlier, large residuals far from the regression line. So you saw the regression line. If any point or data points which are going far beyond than the regression line, those data points can be outliers. You can detect this with the standardized residuals. You can fix the value, you can fix the confidence interval, and beyond that, whatever is going, you can detect as an outlier. It may indicate the data error or the special cases. It's very much important to investigate before removal. You can just see the data points which seems outlier, and it won't make sense. You need to check the data point, why it can be outlier, whether it is providing some meaningful information to the data, and then you should make the decision. Leverage, you can definitely use extreme predictor x values measured by the head values, and you can use the threshold. It can potentially pull the regression line. If you are using the outliers, the outliers can pull the regression line. It it can be very much specific to that particular data set. It might not be good regression model to make some kind of predictions on the new x variables when you will get. Outliers can influence and change the regression coefficient strongly. It can measure the Cook's distance. It can combine and leverage the residual effect, investigate points with anything like Cook's d values, investigate those points, whether those can be outlier or not, how much influence they are creating on the model, how much drag they are creating in the regression line that we are plotting on the normal distribution. Then you can try example of fit and the interpretation of simple linear regression. You have, let's say, advertising data set, annual salary buy is $1,000, advertising spend in the $1,000 in 10 different regions. You will calculate the regression coefficient. First coefficient will be beta 1. Again, whatever value you are getting in the buy after changing one unit change in the x. So what you're doing, you're doing the sum x minus x mean, buy minus buy mean, and then you are dividing it by x minus x mean guys square and sum. By this you will get some beta value for the changes, and then slope you will get for each beta value. You will get the slope. So you will get the beta 1 value, you will use x mean, by mean minus beta value into x mean, you will get a slope. So now you have a slope and you have the intercept. When you fit the model, our fitted model will show the the slope plus intercept into advertising, and this will be your final prediction whenever you will make. Now you will change the advertising date and you will get the sales. So you will predict the sales by changing the different numbers in the advertising, you know, after fitting. So this is a very simple fitting model. You can learn about it as as much as you want. There is no need to learn the formula, but at least you should have the understanding how the model actually takes the data, fit the model, use the intercept, use the slope for making the predictions. Then intercept coefficient, definitely you have the slope. For each additional $1,000 spent on advertising, we expect the sales to increase by 5,200 on an average. So this is your slope, which is telling you about the data. Intercept is 15.6, which means with zero advertising, we predict 15,600 in sales. Considering whether this extrapolation make practical sense or not, you can just check the slope and intercept values and check whether those data is making sense for you by the from the perspective of the problem that you are trying to solve. If that is true, apply this model and make your predictions. Once you will make your predictions, you can access the model fit and significance by using the R square value. 72% of the variance in sales is explained by this model. So this is a good. This can be considered as a good regression model. P value is significant, strong evidence that it is rejecting the null hypothesis. That means it can capture the predictions in the sales by using the advertisement number. Then you can get the residual standard error, which is typical prediction error that you also need to report. Like whatever predictions you will make, on those predictions there is some margin for the error, like the values can go a little bit up and down, and those errors you should also report. Now at last you can verify your assumptions. Once you get your model, once you get your intercept, it is, if it is making biological sense, make the plots, check the plots for linearity, for normality, for homogeneity, for constant variable independence, everything, just check it. Then intervals in the regression that we can learn. It can be mean response is narrower, represent the uncertainty in estimated average response at x0. Prediction interval is wider. It account for both model uncertainty at the same time individual observation variability. So you need to understand the difference. There is a CI confidence interval which you get from the model. There is a prediction interval that you also get from the model, and you get the different response in this. It will tell you about model uncertainty and individual observations that impact for that interval. Both intervals are narrowest near to x0 and as wide and widen as x0 move away from the center of the data. Visualize these shades bands around the regression line effectively communicate the uncertainty to the stakeholder. When you represent the regression line, it should be sufficient enough for any stakeholder to look at this line and understand if we are making any predictions using this model, how accurate, how certain those predictions will be. At last, communicating results. Use effect size on the plot. Avoid overclaiming the causality. Provide assumption and diagnostics. Present coefficient estimates, confidence interval, not just the p-value. Visualize model fit and residual to strengthen your interpretations. Clearly state the limitations and assumptions of your regression model. That is also very, very important. Then you go to the summary checklist, and in which you first, what you do in simple linear regression, you verify the line assumptions, linearity for residual plot, independence, normality, and equal variance. Then you interpret the coefficients, specifically in context of the slope and intercept, how you use the slope and intercept to predict the values, to predict the changes. Then report the uncertainty, confidence interval, p-value, and prediction interval for new observations. And at last, investigate the influential point, examine the standard residuals, leverage values, calculate the distance to provide the information about the influential point also on the regression line, on the regression plot, on the regression model. Quick check. If you'll get R square value of 0.72, tell us about the simple linear regression model. You can simply say 72% of the variation in Y is explained by the linear relationship, with leaving 25 of the unexplained by the model. That can be a very good model if you're explaining 72% of the variance. It depends on the context, it depends on the question, it depends on your hypothesis, that what you consider good and bad. But only R square is not enough. You need to provide CIs, p values, prediction intervals, everything, so that we know the uncertainty about the predictions and all those information from here. Perfect. Now let's move to the module 4.7, and in which we will go from the simple linear regression. So simple linear regression, in which we are trying to understand the relationship between two variables at a time. Now we go to the regression 2, which is a multiple regression. And in multiple regression, we try to understand relationship between the multiple variables. That is pretty much obvious from the name, in which we interpret the coefficients with the multiple predictors, handle categorical variables, intersections, polarity, select and validate model for the overfitting. Now we will consider multiple variable at a time. Again, learning objective for this: fit the multiple regression model, interpret the partial effects, detect and reduce the multipolarity, and select and validate the different models. Model and interpretation. If you remember, in the simple linear regression, we were only having y, beta 0 plus beta 1 and x. So x was one value for us, beta 1 was intercept, beta 0 was slope, and we were predicting the y value. In multiple linear regression, we will have multiple x values. For each variable, you are getting one x value. For each variable, you are getting one x value. If you have 20 variables that you want to fit in the model, you will have 20x, x1, x2, x3, x4. For each x, for each variable, you will have one value. For each variable, you will have the intercept, and then you will have a slope. So each coefficient represent the expected change in the y in the one unit in x, in changing in the x. So here what you are computing beta 1 intercept will be different for each variable, because the changes you will expect in the by the changes in the x value will be different. So here there will be some variable which will be highly important, there will be some variable which will least important, because some variable will change the value a lot, some value will change the variable little less. So in multiple regression, you identify the relationship, you identify the intercept, and at the same time you identify which features or which variables are most important based on their effect on the targeted predictions or targeted variable, which is y in this case. Now, if you will use the categorical predictor, what you will do? So if you have a categorical variable, let's say in one of the predictions you have some categorical prediction of the geographical locations or the product categories or the age, something like that. So you can convert, you can encode those categorical variable into the numerical variable, because in the regression you need all the numerical variable to fit the model. So you can either assign a code 0 1 2 3 4 5 6 categories depending on how many categories we have, and these numbers can be used for the regression fitting line. Then interpretation, coefficient shows differences in the outcome compared to the reference group. You can take the example of region, different regions. When you're using east, west, north, south, you can just create west as 1 by 0, north as a 1 by 0, east as a reference. So those kind of things you can change. I have explained each and everything like this is considered as an encoding. So encoding of the categorical variable. In my Python class, I have taken this data cleaning and data manipulation module. I think it's module 5.2 or something. There you will see I have explained this everything in the detail, how you can encode the categorical data to get the numerical ones to fit the model, to use those numerical data to do the downstream analysis. You can learn about those things. Then there is an intersection, which is also very important when effects depends on the other variable. So intersection is important. It includes one in square 2 to allow the effect of 1 to vary with the effect of 2. Interpretation is for each unit increase in x2, the effect of x1 changes by intersection. So this you need to understand, this you need to note it. When you are working with the very large model, multiple variable, you cannot go in the data points and you cannot get the intercept for, you cannot review each and everything, but you need to understand the concept. Common form can be gender and treatment. Common form can be age and income, price and session. When you see the effect are intercorrelated, both effect are simultaneously can. So you are checking the effect of the gender, let's say on the prediction, treatment on the prediction, but then you are trying to identify the intersection when gender and treatment are all together. What will be the effect on the y? This is a simple concept when you're trying to see two variables at a time. Okay. Plot marginal effect for the clarity, so how slope changes. Use when theory suggests effect vary across subgroups. When you are getting the differences in these groups, you can divide the data, you can plot, you can do the multiple regression analysis for the subgroups instead of combining all groups together. You need to definitely handle the multi-collinearity. Symptoms are there, large standard errors you will see for the coefficient shift sign when variable added or removed. Any variable you will add or remove, it change a lot. High R square, but few significant predictions. That is the just indication that you have multi-collinearity in the data. Then you are getting the problem associated with different kind of correlations. How you can tackle this? Drop and combine highly correlated features. Let's say if you are doing the regression analysis, you have a 20 features. Now out of 20 features, some features have effect on y, some don't have on the y, but then is feature like x1 and x3. X1 and x3 is highly correlated. Whenever x1 is going high, x3 is going high. So effect of x1 and x3 on the y will remain the same. So to tackle the multicollinearity, identify highly associated, highly correlated variable. Consider any one of them, like either x1 or x3, to avoid overfitting of the model. Consider x1 or x3. If you use both, it will again introduce multicollinearity. You will see the overfitting of the data. There is no point, because those are highly variable and those have a similar kind of impact on the predictor variable. By use principal component analysis, apply regressions, center standardize the predictions, collect more data if possible. So these are the remedies to handle the multicollinearity. Then you do the model selection. So model selection, first is the define candidate model. First you need to define the candidate model, that is identify the variable of interest. So if you have in a data, if you have 100 of variables, but you need to first identify which variable you would like to fit in the regression model. You cannot fit all the models if they are not making any biological sense, if they are not if they are not a part of your hypothesis, the part of questions that you are trying to solve based on the domain knowledge, consider transformation is very very important. Do the transformation. If the data range is super wide, transform it, make it little narrower. Interactions, do the variable subset for the multiple candidate models. Then apply the selection criteria. Now once you do this, you have defined your model, then apply selection criteria. For selection criteria, compare models. You can build n number of models by combination of the variables, by different variable subsets, using different type of models. Then you can compare them with the adjusted r square, AIC values, BIC values, and any other values you can compare here, just to measure which model perform best in terms of these matrices which we have already discussed. Then you can do the cross validation. Cross validation is also very good example. So in the cross validation, the ultimate idea is, if you have 100 instances, if you do five-fold cross validation, you divide 100 instances in five parts. Four part you use for the training, and the rest fifth part you use for the testing. And this process you repeat five times. So that means, like, you will repeat this. Now rest four part you will use for training, another part you will use for the testing. So this is a good practice to learn from the complete data, to check the performance on the complete data set. So the random selection of the subset cannot be biased. And it is like, in this you can get the RMSE, MAE prediction, R squares, and this generally avoid the overfitting. Okay. Then you do the final model selection. Once you choose the model which has a good balance, which has a good performance, which has a good performance even on the cross validation, that model is ready for you to process and make the predictions in future. And these kind of models you can make for the predictions on the test data sets whenever you are getting. Quick diagnostic refreshers for all of you. The residual plot, you will check for the patterns, curvation, uneven spread that indicate the model violation. You will check the normal QQ plot, verify normal distributions, straight line is there or not. Then you will do the heterogeneity test. You can test white test, visual inspection, lot of other tests you can do, just to quickly visualize the plots that you are making sense from that question that you are addressing using the regression model. And then you can use the influential point, like examine Cook's distance, leverage head values, or DFF fits for the multivariate constant if you are handling with the multivariate datasets. Quickly about the regularization. Once you create the model, after creating the model, you will just make a plot, do the diagnostics, and then you will go for the regularization. In regularization, you need to use the advanced regression techniques to control the over range. First thing, add a penalty on sum of square coefficient. Shrink all coefficient towards zero, but rarely to exactly zero. Shrink coefficient, put lot of penalties. Then you can do lasso regression. Lasso regression, add penalty on some of the absolute confidence and perform variable selection by shrinking the sum coefficient exactly to the zero. So there are different type of regularization. You can use raise, lasso, elastic net, turning via CV. Ultimately, the the purpose of using different kind of regularization is to avoid the overfitting as much as possible from the data and remove the data bias. You can try all four of them, check the model performance, and you can come back which regularization is working best for your model, for your data set, to answer the questions that you have in that particular project. Try all four. Now example of multiple regression is, if you will remember, we discussed the example of linear simple correlation. Now this is multiple correlation. You have again slope, you are detecting the price, you have slope, you have the intercept for the square feet. Based on the square feet you are predicting the price. So okay, you are just predicting the house prices. Based on the age you are predicting, let's say, the price. Based on the bedroom you are predicting the price. Neighborhood you are predicting the price. You are saying that square root into bedrooms can have the impact on the price, so you are using combination of the features. That's how you can define. So for each variable you will get an intercept, for each variable you will get intercept, for this combination of variable also you will get the intercept. And now by doing this you will get the price variable. This is your final model. So in this final model you will get the coefficient something like this. Intercept is, you will get intercept value is square root plus 150, 250. Each additional square feet add 120 to the price when bedroom is equal to 0. Now you will get age. Each year of age reduce the price. Each bedroom adds 15,000 when square feet is 0. So that's how, like, the intercept values when you are getting for each and everything values. So you find out the direct relationship between the price changes while changing that particular variable. This is your model. Ultimately at the end you will get r square means 82. You can capture the 82% of the variation in the price of total variation by using this model. That means you have captured each and everything. If you want, you can try different combinations also, like you can try the square root with the neighborhood, or you can try these with the bedroom with the neighborhood. If you will try those combinations also, you might increase the r square value. You might capture 85% to 90% of the variance in the data. So ultimately, trying to capture maximum variance, do not try to overfit the model. Use simple approach of slope, intercept, and the variable to predict the y values. How you will validate the result? Again, cross validation, 5-4 cross validation example I told you. Get the mean r square, get the mean rmse, and get partial effect interpretation. The effect of an additional bedroom depend on the home size, and those kind of interpretation you make and you share with the individuals. Common pitfalls in the multiple regression is extrapolation beyond the data range. When you predict something that is even like not in the range of the data that you expect. Prediction when predictions are super unreliable. You do the post selection interface also p value invalid after variable selection, so you are doing some kind of p hacking or something. That is also pitfall. Ignoring the domain knowledge. You cannot ignore just by considering the statistical significance. If you are reporting some statistical significance, it should have some practical importance, it should have some practical implication. That's how you cannot ignore the domain knowledge while doing only the statistical test. And last, the casual over interpretation. Regression shows the association, not necessarily the causation that we have learned with the correlations also. So you get the associations, you find simple associations, but you should be very very careful that it is a direct cause or it is simply a association that you are seeing when two variables are moving together. Summary and takeaway in this, again, multiple regression best practices is interpret the coefficient in contrast to per unit change in x, holding other variable constant. Okay, then diagnose addressing the collinearity that we discussed. Check if there is collinearity, because it do the overfitting. Identify the highly associated variables, remove it before doing the regression, before including them into the regression model. Validate model with proper cross validation, not just with r square. Take the mean r square, mean rmse for doing the 5-fold or 10-fold cross validation. Prefer transparent model over complex one with simple performances. That is also very important. If you can do quick check, how would you interpret the coefficient of 2.5 for x1 in multiple regression model with x2 and x3 also included? You would say 1 unit increase in x1 associated with 2.5 unit increase in the response variable, holding the x2 and x3 constant. And that is very very important if you are not doing the combinations. Multiple regression model is there, other variables are constant, then this variable alone, the changing in this variable can impact how much to the predictor variable. That is your quick intake from here. So this part is done. We have covered module 4.6 and module 4.7 for both simple linear regression and multiple regression. Now I will see you in the next module where we'll discuss about A/B testing.